Right. So we have seen that when we want to calculate the electric field at some point, we have to evaluate this integral. And this integral has a vector inside. We want to be able to do this for any arbitrary shape of the charges. I am a big fan of algorithmic thinking. So what we're going to do now is try to create an algorithm, try to create the steps we're going to think through, and if we get comfortable with those steps, then we should be able to solve any problem given to us. What I'm doing and the way I would do examples is not necessarily a unique way of doing examples or problems. There are different ways you can tackle the same problem. However, what we are discussing now, you can apply it to any problem rather than having to think for every problem on its own. To me, developing algorithmic thinking is the foundation for doing creative thinking after that. You cannot do creative thinking till you have understood the algorithms and are able to do that. Then you can start looking for patterns and you can make your own way through. But if you are just lost in the jungle itself and you tax your brain doing something which can be done very simply, then you'll never be able to do creative thinking. So that's my goal here. To develop the steps we will take in solving and trying to come up for this problem in any specific way. Now remember, what we had said here was k rho dv r square r hat. I could have charge q distributed. It may be even distributed uniformly. Let's say I've charge q distributed over a ring uniformly, and I want to go to a point and calculate the electric field there. Even if the charge is uniformly distributed, it is not the same distance or the same direction. The charge sitting here and the charge sitting here are in different directions and different distances. So to be able to do this integral, we need to know rho v. And this is what our step 0 is going to be. Step 0 is to be able to calculate rho v. And when I say rho v, it also means rho s and rho l. If charge is uniform, if I say charge q is uniform over volume, surface or line, then we know, we have done this in the last week, rho v will simply be q divided by volume. Rho s would be simply q divided by the surface area over which it is there, and rho l would be simply q by l. If it is non-uniform, then I will have to set up an integral. I'll have to say q is rho v dv, and I will have to integrate this. I'll have to put the function of rho v and then be able to calculate whatever constants are there. For example, if I tell you charge is distributed linearly in a sphere such that the charge density is 0 at r is equal to 0 and the total charge is q on that sphere, this is a spherical sphere in the volume, then you can basically say that the charge density is going linearly as rho naught r, but I do not know what this rho naught r is, so I have to set up an integral which would be rho naught r square dr sine theta d theta d phi, and that value should be equal to q. R going from 0 to capital R, theta 0 to pi, phi 0 to 2 pi. And what do you get? You will get 4 pi rho naught r cube, that becomes r by 4 by 4. This 4 pi just came from integral of sine theta d theta, which is 2. Integral of d phi is 2 pi. So I get 4 pi rho naught r cube dr. R cube becomes r to the power 4. Limits there, so r to the power 4 by 4. And that should be equal to q. So rho naught should be 4q by r to the power 4. And 4 pi here. You could cancel one of the 4's if you want. This is step 0. If a charge density is not given to me, I need that charge density before I can evaluate that integral. I'm calling it step 0 because in some of the problems we may be given charge density. We may be told that the charge density is rho naught or rho naught r or rho naught sine theta. We may not be given total charge q. We may just be given the charge density. If I'm given the charge density, I really do not need to do this step at all. So that's why I'm calling it step 0. An example of that where you do not really need is a p-n junction. You know what the charge there in the p-n junction is depending on the dopants you put in your semiconductor material. Alright, and that's your step 0. The next step would be to define your coordinate system. That's why we spent the whole week doing problems with coordinate system. So you have charge, I'm arbitrarily drawing it, and I'm assuming it's volume, but it could be surface or line. You choose the coordinate system and you choose not based on where the point you're measuring it at is, you choose based on the shape of how charge is distributed. If the charge is distributed over a line, Cartesian coordinates make sense. If the charge is distributed over a line which is curved, maybe polar helps. If a charge is distributed, for example, on a ring, polar or cylindrical would be the way to go. If the charge is distributed over a sphere, spherical coordinate system would be the way to go. So you choose the coordinate system and you decide what you are going to, and this decision is based on the shape of this charge. And not only that, you decide the origin of the coordinate system. Where are you going to put your origin? Sometimes choosing the origin can be of great help. You have a ring or a disk. Let's say you have a disk, and I want you to calculate the electric field at that point, right over here. The disk is lying in XY plane, so it is coming in and out like that, and I want you to go right in the middle and calculate the electric field at that point. Which coordinate system should I use? Ring, a disk, circle, polar, there is a z component, cylindrical, right? I can easily integrate this circle with polar system, and then there is a z axis because the point P is up. I should use cylindrical coordinate system. Where should I put the origin? If I look at this place here, there is a disk, things are lying right above this point. Then there is symmetry right around that point P. So my origin should be on this, and this is where I should put my origin, right in the center. That would help the way, that would be the best way to do it. Now again, I have a disk. I'm just giving you the top view now. And instead of calculating the electric field some distance above here, which is what this problem is, I want you to calculate the electric field at this point P. Where should I put the origin? And you did a problem in week 1 which kind of illustrated things for you like this. Over here, if I put the origin here, my life would be really tough, because if I went and I created a differential element, this, if I'm calling this R, I'll have to call this R1, and this would be R1 direction. Electric field would be pointing in this direction. As I change things around, this R1 is going to vary as a function of R and a function of phi. And I'll have to find that function. For this problem, putting the origin here would make your life so much easier, because when you have the differential element, what you are calling R for your coordinate system is the same distance R for your distance from the charge to the point P. This is your point A, this is your point P, right? So putting the origin here would be the best bet. So step 2 is choose the coordinate system based on what the shape of the charge is. How can you easily integrate that shape, and then figure out where to put the origin. And the way to think of the origin is to start thinking of symmetries. Here you have a nice symmetry sitting at that place. Here, when I'm calculating electric field, the symmetry is best maintained when I go and create lines like this. I take a compass and I rotate the compass like this, not when I rotate the compass like that. So origin here would make sense. All right, let's now go to step 2. And as an illustration, I will just take the disk with the point P on the circumference of the disk. And step 2 is on the charge where the charge is present, distributed charge. Every time I'm talking charge now, it's distributed charge. On this distributed charge, choose A, which is the arbitrary point we have been calling it every single time, and define it with coordinate axis. This is your point A is the arbitrary point we have on the charge. By moving this arbitrary point wherever the charge is present, I can account for contribution of the electric field due to these different fans or vacuums which may be present, different charges which may be present. So I have to be able to move this point A, and since I'm using a coordinate system, I should define this as a variable with my coordinate axis. So as I change the variable in my integration, the point A goes to different places. And thus I should be able to account for the complete charge. Right here, not only when I say when you choose A, Yes, you choose a point, but then you have to also think of how you're going to integrate at that point. What limits you're going to get, what are the things you will have to take care of. Going back to the example or illustration, we said we have a disk with some uniform charge and I want to calculate electric field at that point, and we said we're going to put the origin here too. So as soon as I've drawn the origin, it's basically now saying I should put my axis. We always put x and y axis. And because this is a circle, sorry, because this is a disk, polar coordinates help us solve the problem best way. So what we are going to say is we are going to go to an arbitrary point. That arbitrary point is going to be some radius r away and is going to make an angle phi with the x-axis. So the position of the point is going to be r and phi. What am I going to do? I am going to change phi such that I start from here and then I'm going to change phi till I reach this point. So I start from minus pi by 2, clockwise is negative, counterclockwise is positive. So I start from minus pi by 2 and then I go to plus pi by 2. So it's telling me phi has to go from minus pi by 2 to plus pi by 2 when I do that there. And in this place, and what is r going to do? Well, r is going to depend upon my position of phi. When phi is equal to 0, r has to go from this point to that point, which is 2r. When r is equal to, when phi is equal to some angle, then r has to go from this point to that point. Let's call it r max. So r has to go from 0 to r max. R max is smaller than 2r. And similarly, if I go here, r has to change. If I go at phi is equal to pi by 2, r is 0. I'm just writing that small point as with 0 radius. So r has to go from 0 to r max. And as we see, this r max value is going to be a function of phi. So we better realize what that function of phi is going to be. Keep this so that we can now prepare ourselves to integrate, prepare ourselves to set these things up. If we cannot do that, we should not even proceed further and try something else. So r goes from 0 to r max, and we have a nice 90-degree right angle triangle. Look for right angle triangles. R max is simply going to be 2r cos of phi. When phi is equal to 0, this becomes 2r. When phi is equal to 90 degrees, this is 0. Cos phi is 0 and small r is 0. Always nice to check whether things are making sense in these limits. So that's our step 2. Step 2 is to be able to define my arbitrary point where I'm going to define my differential charge and then see how these terms are going to vary when I do the integral. Figure out what these limits are going to be. Step 3 is now a pretty straightforward step. Arbitrarily drawing, or let's just take the example we have. We have said there is a disk. I want to calculate the electric field this is 0. We have defined point A over here with phi and r. Now what I have to do is look for the differential charge which is present at point A. So we look for what is the value of a dq. And a dq is going to depend upon how the charge is distributed. If the charge is distributed in volume, dq would be rho v dv. If it is in surface, rho s ds. If it is in line, it will be rho l dl. The beauty of using coordinate system is that as soon as you decided what coordinate system to use and you spent a full week on this, we know exactly what dv is going to be. If I want to go to spherical coordinate system, dv is r square sine theta dr d theta d phi. If I want to go to Cartesian, dv is dx dy dz. If I want to go to cylindrical, dv is r dr d phi dz. As soon as I fixed my coordinate system, I already should know what these values are. They cannot take any arbitrary shapes. So now, in this case, the charge is distributed over a surface. So we would be drawing a surface element which would be ds, and because we have used polar coordinates, this would be simply r dr d phi. Once we have a dq, then what we have to do is set this integral up. Set what a dE is. Not the integral, just write what a dE is. dE is going to be simply k dq by r square r hat, where r is distance from A to P. Now, many cases, it may so happen that you're using a small r within your coordinate system. Let's say you go to a spherical coordinate system and you use the small r to define the point A with respect to the origin, but point P could be sitting somewhere else. In that case, your A to P cannot be called r again because you've already given that name to something else. You'll have to call it some other term. And then you can basically say this is R1 and this is R12. So do not get confused about these terms. These are just names we are giving, and R in this expression is the distance from the arbitrary point you have chosen on the charge to the point you are measuring or calculating electric field. But there could be times when you have already used R to define the position of A with respect to the origin O, then AP will have to be called some other name. So that is step 3. We have written it here, and going back to our example, we know ds is just going to be r dr d phi. The charge is just going to be rho s ds. Step 4 is where we have to think individually for each individual problem. Up to step 3, we are following very rule-based and algorithmic-based thinking. Which coordinate system to use? Probably the only unique thinking we have there is where to put the origin. But once you have decided what coordinate system to use, you know what the position A is going to be in one of the 3 variables of the coordinate system or axis of the coordinate system, and you know what the differential element is going to be. You don't have any choice. You just have to follow those rules and you get to that point. Very straightforward. Everybody should be able to get to this point with very little practice. Everybody should be able to do that. Really Everybody should be able to do that. If you're not able to do that, I do not know what to say. But everybody should be able to get to this with very little practice. Step 4 is where the thinking begins. Step 4 is what is unique in every single problem. And step 4 is going to be, you have chosen DE. Now consider the three different components, DEX and DEY and DEZ. Consider these three different components in space. When you're doing here, when I'm doing this system, I'm using polar coordinates. But to come to step 4, in step 4, I will have to see that DE, as we have defined, is going to be in this direction, assuming that the charge is positive here. This setup is in polar coordinates. This integral is in polar coordinates. But here we have to break it into Cartesian coordinates. I have to say that this DE is going to have a component in x direction, which is DEX, and a component in y direction, which is DEY. Again, we've called this x hat and y hat. This is in minus x hat direction. This is in minus y hat direction. I have to be able to do this. And then, by symmetry, see if any field of Ex, Ey or Ez vanishes. That when I integrate DEX and integrate DEY and integrate DEZ, would any of these components, when I integrate them, would they vanish? And for that I have to look for symmetry. Think again, go back to the wind and the fan and the vacuum analogy. This is a fan, it is blowing wind around. Is there a chance that the wind will only go in one direction? What that would allow you to do is, instead of evaluating three different integrals, you will only have to worry about one or two integrals. You do not need to do all three different integrals. So instead of doing all these three, you will only have to worry about doing one or two integrals. So that's where we look for. See if there is symmetry, if any of the fields vanishes. If a field vanishes through your looking at the symmetry, we don't need to evaluate it any further. We can just say, hey, by symmetry I know these components will cancel out and life would be nice on this side. I don't need to do an integral, but things will add up on this direction, so I should only set up the integral there. Going back to our problem up on the board, is there any component of z on this plane? No. DEZ is 0, so I can, for this specific problem, I can neglect it. This is a very thin fan, it is blowing air around. Yes, when I go somewhere up of this thin fan, air would be blowing this way, but when I am in this plane, air should be only going around like that. So for sure DEZ does not exist, I don't need to worry about it. But I do have DEX and I do have a DEY. And now I have to start thinking, is there a component which would cancel out of these two components? And again, because this angle is phi and this angle is phi. Well, assume that this disk is uniformly charged. If I assume that the disk is uniformly charged, I can go to a point below And if this distance is r, this distance is r2, and this angle is phi. This point is exactly the same height below as this point was above the x-axis. For the point below, let's put this in here, blue. Which direction is DE going to be? DE is going to be in that direction, assuming this is uniformly charged. If this is uniformly charged, the charge which is present here and the charge which is present here, that charge is going to be exactly the same. These distances are the same, these angles are the same, which means this angle is the same and the length of this vector is the same as the length of this vector. This is coming from here, this is coming from there. If I decompose the top, I would get a vector in this direction and a vector here. And what do you see? These two vectors should be the same magnitude but opposite direction, so they should cancel each other out. Individually, this point, electric field due to this differential charge, does have a y component, but there is another point sitting across it which has an equal y component but opposite to your direction. And thus, dEy is going to cancel out and only the x component is going to remain, and thus even though dEy exists, I do not need to worry about it. I do not need to do an integral. If I do an integral, the integral better come out to be 0. Otherwise there is something wrong I have done. So I don't need to worry about it, and I can only focus on this component over here. And thus I can write this component dEx as we have written. It is going to be this magnitude which is projected on the x-axis. If we call this angle phi, this angle is phi also. So that would be in magnitude equal to dEx cos of phi. And if I want to put a vector towards this, this is going to be in minus x hat direction. That's my step 4. Step 4 is the place where you have to do this creative thinking. If you cannot do creative thinking, if you cannot find the symmetry, then you have to account for all these three terms. Nothing, no harm. You just have to do more work. You'll have to account for all these three terms, integrate them separately, and see what happens. Sometimes things will not cancel out. And in fact, we'll do an example later on where things will not cancel out. That is step 4. Right, let's look at the last step. And this is the time now we are ready to set up the integral and evaluate it. So just again as an illustration, we had said that for a disk where I want to calculate the electric field at this point P, we're going to put a differential element. We said there is going to be dE and only dEx exists. That's the only one which we are interested in because only Ex component exists for a uniformly charged disk. So this is phi, phi. So now we have written, for this example, we have written the expression of dEx. And that expression would have various terms in it. It would have the coordinate axis r theta, in this case r phi, and it would have the distance AP in it. In the way we did it here, AP distance is exactly r, and I don't have to do anything further, and I'm just now going to evaluate the integral. We have already known what the limits are going to be, so we take this and we put this from r is equal to 0 to r max, which we had said was 2r cos phi, and we set up the integral of phi from minus pi by 2 to pi by 2. AP was already r. What if we had not done that? What if we had said that let's put the origin here, this is my point A, this is r, and this is phi. Then I have to call this distance r1. And then when I look at this DEX expression would have the arguments of r, phi, and r1. And before I can integrate, in this case r is independent of phi, r just goes from 0 to capital R. So this integral is 0 to capital R, phi goes from 0 to 2 pi. But now notice what is happening. This r value is a function of phi and r. So this is a function of r phi. As I go to different points, this distance r1 keeps on changing. This is the distance between my arbitrary point to the point I am measuring. So if I get an expression where I have terms, and sometimes they could be angles too, where I have terms which are dependent upon the coordinate axis terms, then I have to write the function in terms of the coordinate axis terms before I can do the integral. Once I do that, then this function DEX, which we are integrating in this specific case in r and phi, every term has been defined with respect to r and phi. Now I am ready to integrate it. That should also tell you why putting origin here was so much better than putting the origin here. Putting the origin here allowed me to use the same r in the coordinate system, this r which was in the coordinate system, to the distance AP, which is from the differential charge to the point you are measuring. So once you get this, whatever component you have, you will have a DE X, Y, or Z component, either of those two, and then you will have some coordinate system axis, and then you may have some distance R1 and some angles involved. You will have to convert these two into functions of your coordinate system, because that's what you're integrating it upon. And once you have converted it into that function, then you can integrate it. Right, so the plan now would be to start with some simple examples and build up over time, and with more examples, this whole concept. We will take these steps as we do these examples so that these steps start to become ingrained in you and you get the message. But obviously, when we are solving the problems, we don't necessarily need to really write all the steps together. Many of these steps can be done very, very quickly. Coordinate system, you look at the shape, you know exactly what it is. You just need to put a point where you put the origin. You don't need to necessarily say, hey, this is my step 1, or this is my step 2, or this is my step 3. I just broke it into steps so that as you practice, you can get this ingrained. And once it gets ingrained, then it becomes a habit. That these things come out automatically without having to think about. So let's do examples. Once you have done the examples, come back to this problem. Come back to this problem. I have given you the steps. I have almost solved the problem. I have given you the steps. I have almost solved the problem. Come back to this problem and calculate what E is going to be for, let's just put uniform charge rho s is equal to rho naught.